So hello everybody for the second session today. A little bit about myself. As you can see probably on the picture that I'm not really 30 years old. Actually, it's just 30 years of experience that I have, especially around real-time data in several spaces like workforce management, security, supply chain, and especially customer experience management. And actually, I'm working as Digital Innovation Officer at DataWerks, which is a highly specialized company on high-volume data analytics, with the goal always to get the data and the insights in real time. So I'm presenting today very special use case that we've done in the area of US theme parks. And happy to see your questions on that, and hope to give you some additional insights on what we did in that space. We cannot name the customer itself because we have contractually limitations to give the name outside. But I would suppose that you get about who it is very quickly when you see some of the slides and some of the numbers and figures that I will present. Okay, so one little slide about us. We are located in Frankfurt in Germany, right across the fair and the fair tower. And this is a very nice building where I'm actually sitting at the ground floor. And we are together, especially with highly specialized data science technology people. Actually 30 people that we are running, and depending on the projects that we are running, we have sometimes a little bit more. But actually we are around 30 people here in Frankfurt. We have as well a location in Orlando, which is exactly the area where we run a very highly sophisticated application with one of our customers. And we started in 2011, especially in the area of terrorist detection, so dragnet investigation. That was our heritage where we started our activities. So we had to deal really with tons of data, and I will give you a little impression about our starting time in 2011 when we started our architectural approach in that area. We have as well a private equity investor who is quite around the corner with us here in Frankfurt, who gave us some additional financial power for the scalability into the future. And our architectural approach itself, we filed that for a patent, for an international patent since a few years. So it's a long time run to give the patent lawyers really the right impression about that technology. I hope I can give you a little bit of flavor about it, mainly based on the use case that I will present today. Okay, our heritage was really in the Arabic area, as you can see with the people here on the picture, where we delivered completely pre-configured application for law enforcement and dragnet investigation. So all the application and all the configuration has been pre-installed on these server racks that we delivered here on that small truck. And this infrastructure runs completely more than 150 billion data records that we run in real time. So it's highly specialized environment that we delivered here. And typically, so from my point of view, I never saw a use case where that kind of volume of data, which is distributed in a large amount of very different and heterogeneous data sources needs to be transferred into a virtual platform. So our original idea is really to pick out the data from the sources and put it onto a virtual platform to make it available in real time and to correlate data from different sources in real time. So this is a little bit a nice expression about how we started and how we had to deal with that type of data. And that type of data, I suppose, will come more and more in the upcoming years as the type of data which makes up the volume in the terrorism detection was mainly based on call data records, who are quite similar to what is produced out of the Internet of Things. So very small, I would say, time-stamped data records with not a lot of input inside of the data records, but it's a high volume of data records. And this type of data will come up in the next years due to things like sensors in machines, sensors in cars and vehicles, and all the type of location-based data that comes up. And this will increase the data itself, or the data increase itself for the upcoming years extremely and dramatically. So we suggest that I would say the typical Moore's law of the capability of and the power of computer will not easily capture that increase of data volume. And if you align that additional data volume to the total global data sphere itself, then you can see that this really increases the total volume of data dramatically. And this type of sensoric data is typically highly sensitive data on the one hand side and very real-time oriented data. So if a sensor gives you information that, for example, a machine has problems with a special part, then you typically would like to react in real time on that. And this is why IoT data itself is mainly driven as a real-time data impression that drives this area where we are specialized in. And to give you a little bit of flavor on location-based data where we are working here in this use case, I give you some numbers, and it's not about the map of San Francisco, but it has some alignments to the map of San Francisco because our customer that we serve in the US has pepped up its major 4 combined theme parks, and these 4 combined theme parks, they have the surface of the town of San Francisco. So it's really a huge area where they put hundreds of thousands of sensors to track people, to track their visitors, where they are walking, and mainly where they are standing in line in front of their attractions, which is one of the big themes where we are working together with our customer to get rid of any types of friction. And you see that there are as well additional areas of business which need to be aligned to what the visitors are doing and help the visitors to get a good experience. So it's all about customer experience in the end, and about revenue that's coming out of that. And for example, one of their main attractions, you know probably well the cinema picture of Avatar, which was, I would say, very, very well known. So the park organization rebuilt the planet of Pandora, and all the 80,000 employees, I would say, out of the 80,000, 60,000 of them are actors who need to be working as an actor where the guests are walk around in the theme parks. So it's a lot of, I would say, workforce optimization activities that we help the customer with real-time data to bring the people at the right time to the right place. And as you can see on the left-hand side, this little chart that is presented on how the waiting times would be today, you can see that the waiting time in front of that top attraction is somehow about 2 hours, which is not so much in compared to the average waiting time. So the average waiting time is way more. So for example, 2 weeks ago I had a presentation where I showed the same slide deck, but with the waiting time graph of that day. And at that day, the waiting time peaks were at 240 minutes. So you can imagine that this means to wait in front of the attraction half a day, and this is not a nice situation for the guests, and even for the park organization itself. It's somehow a thing where they need to reduce the friction that comes alongside with this extreme waiting time. So this is one thing why they invested so heavily in their sensoric data. And beside of that, sometimes even I would say things like a rain shower comes up, which is not so easy to predict and not so easy to get rid of, because the main parts of the attractions, like this picture shows here as an example, are open space areas where the people are they need to see how to get with the weather conditions the best way. So the park organization itself has built tunnels underneath the parks to bring the employees in the shortest possible time to the peaks where the longest lines are there, to get out a little bit of the friction. But if a weather storm like this comes down, then you can see here alone in the picture that people are not very happy with the situation. That even if you do a very nice show, it doesn't help really on the situation. So they looked for something that helps and give them data and information how to get rid of that and how to bring the people in areas where they are covered from rain and weather. And by the way, the hardest thing and the worst thing as well, as mentioned here in the text, is if something like that happens, and for example you are waiting for 3 hours in front of your attraction, and everybody is really upset about the situation, and sometimes the children start to run around, then the situation can get even more dramatically, because then the people are looking for their children, and on the other hand side they want to get into the attraction, and this sometimes needs to be covered as well. So how to find people who are maybe lost, and especially children who are lost. And this is why they created a solution, and I would say the main driver of the solution are these very nice, colorful wristbands that the guests are wearing here. So it's wearables that they use, and they use these wearables to open the doors, to get access to the attractions, to pay for any kind of merchandising stuff that they are buying without carrying around real money. And all of that creates really tons of data, due to the fact that more than 50 million visitors are going through the parks, through these 4 parks yearly, which means a daily visitor coverage of more than 150 people that walk through the parks. And all of these people create tons of data as their movements are tracked based on sensors who get the data of their movements, which is carried on the one hand side with long-range antennas within these wearables, and on the other hand, opening doors or the payment solutions are driven by near-field communication antennas. So there are two types of antennas within one wearable, and that's why they've built this type of wearables, especially for that use case, which costed, on the other hand side, a lot of money to develop that kind of wearables. And beside of that, our customer was, I think, 1.5 years ago, it was the fourth largest supplier of wearables worldwide, due to the fact that more than 30 million people got these wearables, typically 14 days ahead of visiting the parks when they book the parks, and the booking date itself, where you can start your booking, is typically 60 days ahead of visiting the parks. So we are typically covering a scoring time frame of 90 days, where we look for the data, where we correlate the data, and within that time frame, typically around 500 million of data records need to be referenced and picked out of the data sources to get them correlated in real time. And this creates really not just the data lake; it creates more like a like a real data wave that overwhelmed the customer itself, even if they had a very, very good infrastructure. So what they did ahead of the time when we came in, they implemented a huge data warehouse infrastructure, which was really brilliant, as it was one of the leading data warehouse suppliers worldwide who implemented their structure. And as well, they started to implement data lakes to get to quicker results. But compared to the approach itself, from our point of view, it's very similar, because you always collect all the data, and then on the one hand side, in the data warehouse approach, you structure the data into data marts, and with this structuring of the data, which you can see here as the bubbles are a little bit organized in a very nice structure, this means that you replicate the data X times, which means the data volume itself is getting more and more. And the same situation is in a data lake, as you need to replicate the data. If you cluster the data into several areas and nodes to get quicker results. So in the end, your data explodes more than it gets slimmer. So, for example, we have seen a use case where a customer had original 1 terabyte of data in his sources, and in his data lake he had 65 times the volume of the sources data, and this is something that maybe creates a little bit of some special effort for that kind of infrastructure. And typically that data lakes or data warehousing itself is not really prepared for that type of volume that is especially created by sensors. Yeah, they create these very small timestamp data records. So you have a good infrastructure, and that was the situation with our customer as well, with tons of horsepowers, like this tractor pulling picture shows. So there was a lot of power, and even the infrastructure of their data center was really impressive from our point of view, but the results, they came extremely late. So typically 1 day or 2 days, somehow even they got timeouts when they had to correlate not just one person, sometimes when they had to correlate a whole family or a group, a school class, for example, then they were not able to do the correlations due to the structure of the data. So there was a lot of power, but they weren't able to, to run the analytics, which was really a not so nice situation for the customer. So our approach that we think maybe helped the customer, and it helped definitely, was an approach that is a little bit aligned on one area in the brain, which is here in that picture in red color. It's a very small and tiny area in the brain. It's part of the limbic system of the midbrain, and it's called amygdala. So this little tiny thing in the brain, which is a relatively old part of the brain, this tiny part is responsible for detection of any kind of friction. So it's our alarm central point in the brain. And since a few months, scientists have found out that this tiny part of the brain is the part of the brain which detects, for example, faces. So it's our face recognition system, like you use it maybe, for example, with your new iPhone 10, where you have the same technology that is used, and to detect faces, face recognition. You cannot detect all the data of the face. If you have a high resolution picture, for example, and you need to correlate that picture compared to millions or even billions of existing faces or face pictures, you need to use a very slim and narrowed data frame, or here it's more like a data grid. And with this small data grid, you are able to correlate that picture that you recognized compared to the faces that you have in store and that you need to correlate if this is something that is probably gives you an alarm. So typically this nice lady is not alarming, but maybe if it's somebody where you were in trouble when you were a child, then your detection system, your amygdala in the brain, starts to alarm you, and the frame or the pattern that works here is really based on that tiny data grid to get real-time correlations able, and that's what we use as well in our data infrastructure approach. So, and with this small and slim data grid itself, we are able to correlate even through completely different formats, even through very heterogeneous data structures, even through siloed data like transactional data in an SAP application or an Oracle application or whatever it is. If you use a very slim and small data structure itself, you're able to correlate in real time. And this is a little bit the idea behind how we do it. And back to our histories and our roots. This is one of the starting graphical user interfaces that we've built for the terrorist law enforcement areas. So you have typically a map where some pins show you people that are found who maybe are planning something like bringing a bomb into maybe a theme park. So and I would say a situation which is a little bit more complicated, like the people who have accepted to wear a wearable or a wristband. And by the way, the acceptance of these wristbands is extremely high. So I don't know if you can imagine, but the acceptance itself is higher than 99% with the visitors. But this is not the case with people who who try to plan a terrorist attack. So these people try to hide themselves as good as possible. So what they are typically doing, the easiest way to know where they are and where they are moving around is to detect their cell data from their mobile phones that they use. So typically they use mobile phones to communicate underneath each other. But what they try to do is they exchange their cards in the mobile phones very continuously. And the way to get over that is that we not just dig in the data of just one provider, like you can see here with orange. We dig in parallel into all the available telephone providers to see if a person who is connected or who has peers, maybe 5 peers, which communicate in whatever way with each other, and if they exchange the cards, then we can find them due to their profile that they have made based on the communications underneath each other. So if you exchange the card, then we can find them due to the way that they are communicating with the same people again. So this is one area where we need to dig in parallel into different telephone providers. And the second step is that we are looking into financial transactions, so where they are buying stuff, where they are, who is buying what, and where they are getting together to combine some material to build a bomb, for example. And if this is coming up, and the people who are, the agents who are looking for that kinds of profiles, then if they see that people are getting together and probably building a bomb, then they go back to the governmental people and get the approval to get to the third dimensions, which is at the top, to see is there any kind of governmental data available, like visas, like flight data, and things like that, to get to the detailed data of the names of the persons, and hopefully be at the right time to catch up the people before something happens. Yeah? So this is one of the main approaches where we needed to build something new from a data architectural approach, as we had to correlate data in completely different areas and completely different structure and completely different volumes. So you can imagine that the highest volume is based on the telephone data, and then the other areas are not so high of volume, but somehow not so easy to correlate the data. And areas where we are actually develop our applications into more for the future is to help, for example, car assistance applications to get easier in learning into new environments or new streets or new towns where they move in, not to drive several times through the same road to learn about the road, but give these vehicles actually and in real-time information to learn easier about driving through a new town or driving in another country where other rules are set up or traffic lights are completely different and things like that. So to get rid of any friction in that area based on these narrow data patterns that we use and that we can bring in these use cases and areas. And a little bit more about how it really works and how the approach goes is easily to give you an example based on a flight ticket, because a flight ticket looks very similar to, for example, a booking data record when you go into a theme park. So you have all your attractions that you have booked, maybe meals, maybe hotel rooms and things like that, and it's probably a little bit similar like a flight ticket, as you can see here. And there are some areas, especially unique identifiers in this data record, which is, for example, the ticket number or the booking reference. And the rest of the data fields within this data record, they are not uniquely identified. They are just in a row additionally put into the data record as a complete set of data. Which means if we need to correlate data in that types of data records, then it's not easy because it takes time to walk from an analytical approach through the whole data sentence itself. Yeah? So the idea that we are starting on is, on the one hand side, get together with the customer or with the experts to see what are the data that needs to be correlated for your use case itself. And then we mark that data to find it always back, and in any case to use it as a locator itself. So it's a mapping approach where we have built microservices to get that done automatically. And then we pick that data field out of the original data source so that we are not belonging to the data source and the restrictions of the data source. And with this approach, picking out the data field, we give that data field a unique identifier if there is not already a unique identifier added to that data field. And with this unique identifier, we need as well a kind of synchronization approach, how often the woodpicker can pick out new data out of the original data sources, not to bother the data source itself too heavily with any kind of actualization activities. And then we are able to correlate that picked data with actual information. For example, to give you the right seat at the right time. And maybe if there is some friction, like overbooking of the flights, and even this type of data could be used in real time to see if there is another flight available and give you a according seat in maybe in another plane or with another provider. So this is one of the use cases where you can see a little bit the approach which we use. And what the customer itself is now able to, with this approach, here's one very fancy example where they got already some awards, how they treat their customers in a completely different and magic approach, is that now they know about is a customer or a group or a family is approaching a restaurant, and if they know, okay, they are approaching a restaurant, we get the data, what they already have reserved, and what they want to eat, and what they want to drink, and the kitchen already started to cook, and when they found their seat, and underneath the desk there is a sensor which gives the real-time data about who is really sitting at on what desk, and then you get your meal immediately when the last person had sit on the table. So this is one of the magic moments that's come up. And the other idea, and especially the main use case, was how about standing in that line half a day? How to get rid of that? So the idea was, after getting some data and getting step by step a little bit more intelligence into the results, was how about giving the guests a free voucher for any kind of trouble, for any kind of standing too long in a line. So we see and we detect how long are people standing in line, and they can deliver them a voucher on their mobile phone or whatever device they use, and offer them some free stuff in their merchandising shops. And this gives, out of a friction situation, more a positive situation. And out of that, at the beginning, the customer had really problems to know about, I would say, who has really the, as this little statistic shows, who has really the purchasing powers on. And as you can assume, in a park, not the not the father or the mother has the pants on. It's the children who decide what to eat, where to go, and what to buy. Yeah, so they are the deciders, and there was absolutely no historical data about what children want and how they decide and how they feel friction and how they react on that. So they had really to collect that data from scratch, and that was the reason why they invested so heavily into their sensorics environment. And now, as you can see, even not showing who it is, but you can still imagine who it could be. So it's tokenized here, but our customer is really the world leader in merchandising business. Yeah? And within the project itself, we found a very nice article in Harvard Business Manager last year in a special edition, where it was mentioned that our customer already could add additional visitors into the park by a percentage of additional 30%. And what is even more from a business perspective, a positive result was that they got additional revenue of $500 million with a margin of 20%. Which means 100 million additional profit based on the real-time data that they use now to create merchandising revenue. You know? So it was a little bit by accident that we found that article because the customer itself didn't inform us about that. But this is typically if you jump in as a firefighter into a project. You don't get these types of information, and we were very lucky to get that information directly from that article in Harvard Business Manager. And back to the project itself, some information around that. They went live in August 2016, and we started the project just with one on-site expert that we sent over to the US. And he went over with a desktop PC, with a Unix desktop PC with a pre-configured environment on it. And the park organization people, they told to our expert if he's completely crazy, what he's thinking to do with this tiny desktop PC. And he said, yeah, let's start, let's see. And they said, hey, to give you an information, just a few weeks ago, one of Gartner's most admired expert in data virtualization and data collection was here, and they came up with a huge environment, and they were not able to help the customer. So they were a little bit unsecure if this is really somebody that you can trust in, but luckily he could within a few days he was able to connect to the data sources and show them the first results, and then after a few days they told him, you don't get out here until we see what's going on. And step by step we added data source by data source. So it was somehow, today you would say it was an agile approach, a learning approach, by adding data source by data source. And actually we have now connected 42 data sources in total, and we closed the complete project within half a year net project time. And as I said, just one data expert on site, and 4 data experts who built a business rules engine within the last 6 weeks of the project. So that was, I would say, compared to the situation, a very, very slim project approach, and that's why we were far below $500,000 project costs itself. So the return on investment was really dramatically high if you see the profit that came out of that project. And the approach is, I would say, mainly driven by a strategic approach, which is used, for example, in the Blue Ocean strategy. Maybe you heard about that, where if you focus not on the mass of data, if you focus more on the proportionate influence factors, which are most tiny factors, then you are able to get, I would say, the real results and the reliable data to help yourself in a very slim and quick approach, at low cost. So the idea, once again, is if you see the data sources on top who create data, and data in the big bubbles has always data fields within. So we look together with the customer, with some business experts, what data is really relevant. We pick that data out, and with that process, we reduce the data volume by typically around 90%. So only 10% left from the original data volume, so completely the opposite of what's happening typically if you use the original extract, transform, load approach, which is used on data warehouses, or extract, load, and transform approach, which you use at data lakes. So with that reduced and essence of data, you are able, if you've done it right, you're able to cover even more than so typically it's 97 to 98% of all queries and joins that come up from the data consumers, that they are answered by that special approach of extracting the right data out of the data sources. Yeah. So our, I would say, message is somehow, if you collect all data, that means you typically just feed the data recycling industry. Yeah. So you collect too much data, and you get in problem with all that data. So if you do it a little bit different and identify the relevant data directly in the data sources, then you are able and capable to act and react. Not only react, it's more like an active acting. Yeah, that is from my point of view. I thank you very much for listening to my explanations about that project, and happy to answer some questions if they are coming up in the meantime.